So it's a pleasure for me to introduce Adam Kucharski. The title of his talk is Using Mathematical Models to Generate Better Pandemic Insights. First of all, I would like to thank Adam for accepting the invitation to be here with us today. So Adam is an associate professor and a Sir Henry Daly Fellow at the London School of Hygiene and Tropical Medicine. So when we think, he also had previous trainings at Warwick, Cambridge, and Imperial. So they are all three very strong programs in mathematical modeling of infectious disease. But when we think about the London School of Hygiene and Tropical Medicine, we always have to mention the work of George MacDonald. So my background is in malaria, and so this is a very influential work, and it's at the basis for the modern modeling applications in infectious disease. So there is a lot of tradition since the time from George MacDonald, and the modern Center for Mathematical Modeling of Infectious Disease, the CMMID, to which Adam is also affiliated. So Adam published on a number of topics and in COVID-19, so the first working the basic reproductive number, the estimates of R0, the overdispersion, and the impact of non-pharmaceutical interventions. So all the early work on those topics, we can see the signature of Adam in them. And he also published a book, The Rules of Contagion, that received very well reception among the critics, and it's a very interesting book. And most of all, Adam is a fantastic speaker, so I had the chance to see and to watch his TED Talks and the TED interview. And what I like most is his acronym for the factors that enter in the calculation of the R0. So he coined this DOTS acronym for the duration, opportunities, transmission probability, and susceptibility that I have been using with my students since then. So Adam, it's your turn now, so I'm handing over to you. And thank you very much for accepting our invitation. So I am stopping sharing this slide and
Okay, well, thank you for the invitation. Thank you for the kind introduction. I'd like to talk about a number of different aspects of work relating to using mathematical models to improve how we understand pandemics. So the different features of pandemics they can help us with, but then also some of the limitations, some of the big challenges I think that there still are when it comes to this kind of work. So I'd like to start just by acknowledging all of my colleagues who've been involved in a lot of this in the Center for Mathematical Modeling, this big working group, and then of course all of the collaborators and partners around the world. So a lot of what I'm presenting is a big team effort, a lot of it led by the people who've done a huge amount over the past 18 months. And I want to sort of divide this talk into four sections, focusing on these different aspects of how we use models. So starting off with the basics, how do we actually just understand some of the fundamentals of what's going on? Talk a bit about how we understand real-time situational awareness. When things change, as they often do, how do we make sense of that? Talk a bit about control scenarios, how we can estimate different measures, and then also just think a bit more broadly about this kind of work, how it's been used in the pandemic, how can we do this kind of open science better in future. So first of all, in terms of understanding the disease dynamics, one of the big challenges we have during an epidemic is we can't observe actually what's happening. We can just observe measurements of that from various data sources. And the big problem, particularly early on, is that data isn't very good. So every epidemic I've worked in, you have a lot of problems with the data. They're often delayed, they're biased, they're incomplete. And I'll talk a bit about what that looks like and how models can help us deal with some of those limitations. So the first big one is just the delays in data. You're never actually seeing the epidemic. You're seeing the results of what was happening a period of time ago. So if we have someone infected with SARS-CoV-2, as we all understand now, there's this delay incubation period between symptom onset and then a delay perhaps if people get tested. There's a delay between infection hospitalization, and there's delays between infection and death. So all of these events that might be easier to measure aren't actually telling us what's happening now. They're telling us what's happening possibly quite far in the past. But on top of that, data isn't necessarily going to be complete or unbiased. So this is a really nice paper from last year that outlines the change in how COVID-19 cases were defined in Wuhan early on. So in the start of the outbreak, the cases were defined quite strictly. There were pneumonia cases, some of them with links to the market. But then the case definition changed. There was this version 2 that appeared. And when that happened, the records were backfilled. So in other words, the data set in hindsight was actually updated. So the current version of the data set wasn't actually the same as the one in the past. And then we had this version 4. I'm not totally sure where version 3 went, but I think there was a series of changes in a very short period of time, and then a version 5. So you can see from these approximate curves, if they'd stuck with version 1, then you would have seen this much shallower epidemic, much lower numbers of cases. But of course, these updates broadened the people who are included in the data sets and gave a different curve as a result. And this was all happening over a very short period of time, which obviously makes it difficult to understand what's going on. So it's very valuable in real time to be able to compare multiple data sets, ideally ones that are orthogonal, that are giving you information about different parts of the epidemic, and then having a mathematical model that can act as a structure to bring together those different data sets. So a really useful early example of this relating to the Wuhan data was this study by Imperial College. So the situation at the time on the 16th of January 2020 was there had been 41 cases confirmed in Wuhan, but 3 cases of this novel virus had been detected abroad. Now, of course, that's quite a lot of cases to be detected abroad if there's genuinely only 40 cases in Wuhan. Because you imagine the average person in a city is quite unlikely to travel internationally on a given day. So what you can do is build a simple model that looks at international travel patterns out of Wuhan. You can estimate what proportion of the city might travel on a given day, and then do a back calculation. If you've detected 3 abroad, if you've got this proportion that are traveling daily, how many might there be in the city? And this estimate by Imperial, a simple calculation, but really powerful one, showing that there'd probably been thousands of cases already in Wuhan at that point. And sure enough, we saw the data being updated. And the reason this was a useful insight is because internationally, there was a lot more sensitivity to finding cases than perhaps there was in the city where there was a larger outbreak. So in other words, you had 2 data sources that weren't providing exactly the same information, and it meant you could get a better insight as a result. So conceptually, we can think about this in terms of a model structure. So a very familiar model structure when you're dealing with epidemics is an SEIR type model, where people start off susceptible, they're exposed, but not necessarily infectious yet. They become infectious and they recover. And we can have many different versions of this, a lot of complexity about different aspects of the population. But fundamentally, these are the different disease states that we're going to be generally interested in. And if we just look at the case data being reported, we're basically just observing this transition in this model, because we're observing people who are becoming symptomatic. And then if they become symptomatic, they might go and get a test and be confirmed and show up in the data. Often they won't. But you've got this quite large, well, relatively large dynamical system, and you're only observing one transition in it. So that's quite a difficult statistical problem, and it leaves quite a lot of unknowns and quite a lot of uncertainty. And so one of the benefits of combining data is you can start to try and narrow down some of those possibilities. So for example, if you look at international data, particularly in countries that have a lot of surveillance of travelers coming in, then even if only a small proportion are being confirmed, say within Wuhan, you can pick up more that are being confirmed internationally, and as we saw, allow an estimation of the size of the epidemic. But there's other data sources we can use as well. So quite often during that early period, there were screening tests of people, for example, on evacuation flights. And so that gives us an insight into a different part of the model. It's this I compartment. It's who's currently got the virus. And then in the longer term, we can do things like serological surveys. We can take blood samples, look at markers of prior exposure, and work out who is in this R compartment. And all these different data sets are giving us slightly non-overlapping insights into these compartments and a better understanding of these dynamics. But of course, in the early stages, we didn't have serological surveys, so we were reliant on these other data sources. And that's what we used a lot early on, as did other groups, to try and understand the dynamics in Wuhan. So that the cases that are being confirmed, these screening tests, these international travelers, what could we tell about these different data, and essentially which conclusion would they pull us towards? And one of the big early questions when Wuhan went into lockdown was, what effect had it had? And of course, now the answer is obvious. You can look at the case curve, and there was a reproduction number. Early on, the mean was estimated at about 2.4, so each case infecting about 2.4 others. And at the peak, as you'd expect, each case is only infecting one other because you've got a plateau and then a decline. But early on, the data was extremely noisy. As I've shown, the case definition was changing a lot domestically during that period. So we brought together these different data sources locally and internationally. And then we used this sequential Monte Carlo method that allows us to estimate how the reproduction number might change over time. So you're not putting a kind of constraint in it, you're allowing the model to try and find its way through the data. And one thing that jumped out was there's this quite substantial drop around the time this lockdown went in. And we estimated it dropped down to about 1 by the end of January, which is roughly where the later data would show. But crucially, we estimated that only about the 95% interval was about 4 to 7% of Wuhan. So there was a lot of susceptibility. This wasn't an epidemic that declined because of loads of immunity. It was a large outbreak, but it wasn't that large. And subsequent data would, from serological studies, would match that. So it's an illustration that you can gain these insights into bits of your model and bits of your dynamics, even if you don't actually have the data to directly observe it. And these kind of techniques for adjusting for these delays and these biases in data can be really important. And obviously, one early question was just, what's the reproduction number? Has lockdown worked? But another massive question was actually, how severe is this infection? Because one of the challenges early on is there's delays between people becoming ill and, as I said, a fatal outcome. And so, as an example, this is from a few years ago, but I think it just illustrates the problem we're dealing with. This is data from an outbreak of Ebola in Yambuku in 1976. So it's a very well-studied outbreak. And you've got the cases here in black, and you can see that they peak before the deaths. And that's because you've got this delay of about a week or so between someone becoming ill as a case and then dying if they end up dying of the infection. And the problem with this is that if you just look at the ratio of cases to deaths at a given point in time, you're going to get a biased estimate, because you're going to have cases that have appeared, but you don't yet know what's happened to them because you've got this delay to the outcome. And what that means is, if you just do a simple ratio calculation, so this kind of naive calculation where you just take the number of deaths so far and divide by the number of cases, early on, you're going to really underestimate the severity of your infection. And then as we find out what's happened to those cases, this value, this fatality risk increases and increases. And of course, it's just an illusion that the epidemic isn't changing. And if you only focus on the people where you have the detailed data and you know what's happened to them, you get this correct estimate, which for Ebola is much higher. But there's a second problem here, that for something like COVID, not only have we got these delays, as we've seen, we also have massive underreporting. So we only see a small amount of our outbreak. And the problem with that is early data and early estimates of severity can be very far from what's actually going on. So for example, if we look at an early report for COVID-19 in China, this is just the number of confirmed cases during a given time period and the number of confirmed deaths. And then in this report, the case fatality rate is just the ratio of these two things, just one divided by the other. And what you can see is that the more recent data, where we haven't had this time to wait and see what the outcomes are, the case fatality rate is quite low, and it increases the further back in time you go. And that's because the further back you go, the more likely it is we know what's happened to those cases and their outcomes. And that means that actually, if you look at the earlier cases where we've had this delay and we know what's happened to them, it suggests that the fatality rate or fatality risk is about 15% based on this initial data. And of course, in this period, this isn't what we were seeing internationally. This seemed too high, but that's what the raw data were suggesting in China. So a lot of early modeling work was actually just finding ways of adjusting for this. You know, we had this delay, we had this underreporting, and using models to try and adjust out and come to a more sensible value. And 3 studies did this. There's one by a Hong Kong group, one by Imperial, and one that we did. 2 of them used this screening test data from flights, and then we used some data from the Diamond Princess cruise ship, where there'd been a lot of testing, and then adjusting for the age groups on these in these kind of different data sets, adjusting for the delays, adjusting for the underreporting. We actually all converge on quite similar estimates for the fatality risk for people who are symptomatic. And then the studies for infection fatality risk, again, converge on these quite similar values, which, given this was done in sort of February last year, have held up pretty well in terms of the more detailed data we've since got. But again, it's really making use of these different data sets that we have early on and adjusting to get a more plausible value, because obviously it's not a 15% fatality risk, but still a 1.5% value, as we've seen globally, is one that can cause a huge amount of problems. And as well as these population values, early on, we're also very interested in finding out more about the individual level dynamics. So here we're talking about the reproduction number at the population level, we're talking about the average fatality risk, but there's also a lot of individual level patterns that were spotted very early on. For example, in the UK, there was a lot of coverage of this ski trip in France in early February, where one person infected a lot of others in a ski chalet. And if we look at more detailed data from Hong Kong, this is later in 2020, you can see in the transmission chains, there's a lot of variety. So each dot here is a case, and then the arrows show the likely route of transmission. So you can see that a lot of these cases don't infect anyone, and there are these handful of events where a lot of people end up getting infected. And there's a couple of ways we can try and understand that individual level variation in transmission. So the first thing that we can do is to actually get this kind of data, these transmission chains, and analyze the secondary case distribution and try and fit a statistical function to it. So if you've got this index case, they generate a given number of secondary cases. And if you have lots of those events in your data set, you can work out at the individual level how much transmission there is, and you can fit a distribution. And then you can work out properties like the extent of overdispersion. And this study estimated that about 80% of transmission events come from about 20% of infections. So it neatly lines up with this 80-20 rule that we see for a lot of other infections too. But again, a problem early in the outbreak is you don't have these wonderful detailed data sets always. But what you often do have is information on the overall outbreak. Early on, we were seeing a lot of cases would arrive in a country, you might get a cluster of infections, and then it doesn't go any further. And what you can do in this situation is put together a branching process model and calculate the chance you would see those kinds of distributions of outbreak size given the characteristics of individual level transmission. And this paper by Seth Bloomberg and James Lloyd-Smith is a really nice summary of the theory behind this, because you get some basically really neat analytical results, which you can then use to calculate the characteristics at the individual level. So if you have these outbreak sizes, you can fit models to that distribution and then get at that same underlying individual level transmission. And that's what some groups did early on, and we did some analysis around that. Again, estimating about 80% of transmission comes from that minority of infections. But really, the overall message is, again, trying to use models, sometimes quite simple models, to make more of the early data that you have available to understand these parameters that we're really interested in. And another aspect that's really important for pandemics is not just these kind of overall characteristics and looking at historical data, but of course is what's going on now. And a lot of the work that we've done has been very responsive to rapid questions of, well, where are we now in the epidemic? And I just want to give an example of some work that happened a couple of months ago before talking a little bit more broadly. And this was the B1617 variants, or one of them is now known as the Delta variant in the UK. And this was the data as it looked like on the 7th of May. So this is a report from Public Health England, which is the public health agency in the UK. There were two. So there was 617.1, which actually had a mutation that people were a bit worried about at the time. And India went on the red list on the 23rd of April. So this is the data that, as it looked like in real time. You had some travelers, you had a lot of people that it wasn't clear under investigation. And then what would become the Delta variant, you had what looked like more of an increase in cases coming up to this red list date. But if you look at the data for India at this during this period, India was experiencing an exponentially growing epidemic up to this red listing date. So if you were looking at this data, what would you conclude? And I think a lot of people ask sensibly the question of, well, is this actually an epidemic that's growing in the UK? Or are we just seeing something that's reflecting an exponentially growing epidemic in India? And if we're importing cases at a given rate, that's just being reflected in the case data. And this is where models can be very useful, because a model allows us to lay out those assumptions explicitly and see if it's plausible we can explain that, if that's what's really happening. So that's what we did during those few days. We took data on the case dynamics in India. We took data on the proportion that were Delta in India during that period. We took travel data on the rates we knew that we had importations from India during that spring. And then we put together a simple branching process model where you basically had importations coming in, and then you had these transmission chains establishing in the UK. And then we fitted the model. So here you've just got a simple schematic where you've got some black line of some imported cases in the model, and then we allow the model to simulate outbreaks taking off as a result. And what we found is it was very difficult to explain the data without substantial local transmission. And we found that if we had the non-Delta, the local variants declining, which they were during that period, then you really needed Delta to be increasing exponentially to get this proportion of Delta in the data as we were seeing it. So we were seeing an increasing number of the cases in the UK being identified as Delta. So it went from very low levels up to about 20% at the start of May. And the model suggested that the reproduction number was comfortably above 1 and probably around 1.6 during that period. And sure enough, that's what we saw over the coming weeks. We saw that increase in Delta as a result. So very simple model, but shows that we can use that as a way to actually test our hypothesis. And in this case, very strong evidence that it wasn't just imported cases. And what we did over the next couple of weeks is looked more at local areas and looked at the ratio of, well, what's the R currently for these Delta strains? What was the R for the existing variants? And the ratio typically came out somewhere between 30 and 60% higher. So again, quite a lot of, you can see a lot of uncertainty there, but really pointing towards this is something that's spreading more easily, and a number of other groups were finding similar results. And some colleagues of mine did some really nice analysis looking more at the local level. And by a remarkable coincidence, one of the genes that's used in the test for SARS-CoV-2 in the UK looks for an S gene, and that's part of the sequence where there's a difference between the old variant and the Delta variant. So that basically allows us, if I just zoom in on one of these plots, if you've got less of these tests coming back with this gene, then it means that you've got more Delta. So if you've got this target failure happening, it means you're probably dealing with Alpha, the old variant. If you haven't got these target failures happening in the test, it means you've got more of the Delta. And then these are all of the local areas in the UK. They're colored by the different regions, and it's just calculating the reproduction number for these different areas. And what you can see is that typically areas that had more of the old variant had smaller reproduction numbers, and ones that had more of the new variant had a bigger reproduction number. And if we just go back to that overall figure, you can see that from February onwards, we move from a situation where everything has quite low transmission and lots of the old variants, and then moves upwards across the plot into a situation where we have a lot more transmission and a lot more Delta. And over the next few weeks, that would nestle very, concerningly in that area with high reproduction numbers and a lot of Delta. So again, just another way of trying to make sense of the data that we have available at that finer scale. But one of the challenges when we're talking about reproduction numbers is also just what we're measuring, because it depends a lot on the data source. So that the data I was showing you there was for cases and Delta sequences amongst those cases. But this is some work by colleagues of mine looking, this is recently in the UK. And if you estimate R based on test positives or hospital admissions or deaths, you actually see quite a bit of variation. And the reason is obviously those events are happening in different groups. And so even if you adjust for the delays, you won't always get an exact correspondence, because where people are testing positive, those groups might not be the same ones that are later ending up in hospital. And one thing that happens in the UK to try and adjust for all of these different uncertainties is that every week a reproduction number is produced, but a lot of different modeling groups are involved in that. And then working with government advisory groups, these are combined into a single estimate. So some papers here that explain in more detail what happens, but essentially there's a large number of candidate models, each using different data, using slightly different approaches. And then those are combined, in this case, with a maximum likelihood, restricted maximum likelihood approach to try and get some consensus estimate across all those different models. And what that means is that if you have one data set or one model that there's an issue with, or isn't reacting quickly enough to the data, you have other models to hopefully pull that overall in the right direction. And this, similarly, for a lot of the Delta analysis, was used to provide these kinds of consensus estimates. What I'd like to talk about is probably the most headline-grabbing bit of modeling during the pandemic. So as I said, there's a lot of areas that models provide a lot of insights to, but the big focus, I think, has been on control scenarios, the what do we do and what's the epidemic going to look like. And first of all, at the individual level, I think there's obviously focus on things like contact tracing, but the fundamental problem we have with this virus is that we have an infectious period before people become symptomatic. And that means that if you have an individual that becomes infectious, they can infect someone else, they become symptomatic, they get tested, contact tracers come in. But by this point, the person they've infected may well have become infectious already, and then they've gone off to infect someone else, and so on. And this chain of transmission can very quickly get ahead of contact tracing. And we're seeing this for Delta now, that even countries that were doing very well are really struggling to keep up with the this transmission process. And early on, we did some analysis, again, just taking this process in a branching type model, and finding, as you might expect, that for a disease where you have transmission before symptoms, this was done back, the work started at the end of January 2020, when we had no real idea what these parameters were. But we thought a pessimistic value was about 30%. And this may actually have been optimistic in hindsight, based on subsequent data. But we found that as soon as you have a lot of transmission before symptoms, you need to be tracing a very large number of contacts, because of course, if you miss them, you just get this next generation of transmission and it keeps going. And unfortunately, that's what we've seen in many countries. They've needed more measures on top to come in. And that's where a lot of models have then been employed, that if this alone won't control the outbreak, what other measures might be needed? And a lot of the models here have combined a lot of the insights I've showed you already. So things like those parameters about, what's the reproduction number, what are the different delays. We can build in social mixing data, so different age groups in the population. And then we can have a transmission model. So often we have age structure because that's so important for social mixing, and we see such variation in disease impacts. But of course, we can put spatial structure, we can put anything that we think is relevant in there. We then typically have a disease burden model. So taking a transmission model that looks at infections and then converts it into severity. So what's the hospitalization burden going to be? What the number of deaths going to look like? And some early work that we did, and Imperial were doing this similar work at the same time. Again, this approach with multiple groups to try and find a consensus. And we found that lighter measures, so just having school closures or just trying to shield older risk groups, wouldn't be sufficient to prevent really, really large numbers of cases and hospitalizations. And that's, I think, what we've seen in many countries, that actually it has required more stringent measures over a prolonged period of time to reduce transmission. But these models were developed before there had been a major outbreak in the UK. This was done really during February and early March 2020. And once we have an epidemic that's happened, we can then add some more steps into this process, because we can fit the model to past data. We can make sure that it's saying something sensible about the past, and then we can simulate forward into the future. And this is what subsequent work has done. Just give you a couple of examples. This on the left was some work last autumn by colleagues of mine, looking at these short circuit breaker lockdowns. And it ended up going in at the end of October, this lockdown's introduced, but it was showing that if you fit to the trend, then if you have no lockdown, you'd have quite a large number of deaths, but a sort of 3-4 week lockdown could push that curve quite far into the future. More recently, there's been scenario modeling around the step 4 reopening in the UK. So this was a series of reopenings, and step 4 was essentially most social distancing measures were relaxed in a lot of different venues. And this is the modeling in early July. So you can see this was when the modeling was done. This is what subsequently happened in terms of hospitalizations. This plot's from the 19th. And these are the sort of uncertainty ranges in the models. So you can see that a lot of the models generally would predict a relatively low, long peak. But there are some scenarios we could get much higher peak, much lower peak, really illustrating there's a huge amount of uncertainty, depending in particular in these scenarios about behavior. Do people go back to normal quickly? Are they cautious for longer? When do schools go back? You can see, in September, we might have some increase. And I think it's going to be really key over the coming weeks to work out which of these scenarios we're in. Things are looking lower currently, which is reassuring. But again, it's that uncertainty about what happens next. But I think when we're talking about these kind of models, one thing that I found often interacting with the media is there's this confusion between a forecast and a scenario. And a forecast, generally, we would define as something that we think will happen. So over the next 4 weeks, I think there's going to be this many hospitalizations or deaths, for example. But a scenario is a tool for decision makers. It's kind of what could happen given a particular set of assumptions. And just to illustrate this, a couple of headlines from last March in Germany. One was saying that 60-70% will become infected, according to Angela Merkel. And another, which was probably a more accurate reflection, said, well, they could become infected if the epidemic wasn't controlled. And you had this simple SIR type dynamic. Now, that's a very different message to people, saying this could happen, but we can do something about it, versus this will happen and it's inevitable. And so I think it's really important to distinguish between what's a suggestion of an inevitable outcome and a suggestion of what could happen, but we have the power to influence what may result. But of course, a lot of measures came in, and that created a lot of debates about what actually happened with the epidemics. And this brings us on to, I think, a really fundamental problem that ties together a lot of what I've said. And that's one of identifiability. That if you look at a particular data source, often you don't have information to distinguish between scenarios. So here are 4 different models. These are all, I've coded them up. They're all different model structures, but I've tweaked the parameters so they produce exactly the same outputs. And they all have different reasons for the epidemic ending. So on the top left, we've got just a standard SIR type model. You get accumulation of immunity and the epidemic goes away. On the top right, there's actually quite a lot of pre-existing immunity in the population, but transmission is slightly higher. And again, you see a bit more immunity accumulated and the epidemic ends. On the bottom left, you see actually not that much immunity accumulated, but it's a reduction in contacts. So it's a much smaller epidemic. So I'm making a different assumption about the reporting rate because the ones on top are much larger epidemics. But again, I can reproduce that same curve by adjusting these parameters. And then at the bottom right, contact patterns remain the same, but we assume that the transmission per contact varies. Perhaps the virus just doesn't survive as well outside the host. But again, you can get that exact same curve. I think a lot of the arguments last year about what was going on with the epidemic boiled down to this situation, that if you just look at the case curves, you can come up with all of these explanations and you can develop models that will produce all of these results. And one of the ways we can think of this is in terms of what influences the reproduction number. So as mentioned in the introduction, I think a useful way of thinking about reproduction number is in these 4 components. That if someone's infectious, what's going to influence the average number of people they pass it to? Well, obviously depends on how long they're infectious for, the duration of infectiousness, depends on the opportunities, how many social contacts they have. It depends on the transmission probability. So what kind of, are you indoors, are you outdoors? What's the weather like? And then also the susceptibility in a population. So how much immunity is there? How much vaccination? And the shape of an epidemic curve depends on how R is changing over time. And the plots I showed you are essentially just changing different parts of this dots framework. Because if we multiply these things together, you get the value of R. So of course, you could just reduce susceptibility or this transmission probability or the contacts. And these will just trade off. And unless you actually have information, it's very hard to know which of these in particular is influencing R. So a lot of work that my colleagues have been doing is to try and measure these things, because of course, if you can say what some of these values are, it's clearer what's driving your outbreak. So some work that's been going on throughout the COVID epidemic is contact surveys, just asking people how many social contacts they make and seeing how much it changes. And this is by age group. So this is the participants in the study along the bottom, and then just how many contacts they're reporting along the y-axis. And you can see pre-COVID, kids in particular, loads of daily contacts, particularly with other children. And then post-lockdown, a massive drop in interactions. And if you use that to estimate what the R naught is, post-lockdown, my colleagues estimate that if you look at all social contacts, so including conversations and handshakes and anything that you define as a something where you say a few words to someone or you have some kind of contact, the R naught probably dropped to somewhere between 0.5 and 0.8. So a lot of uncertainty, but it was below 1. And that's the crucial insight. And at the time this survey was done, this was late March 2020, cases were still going up, hospitalizations were going up. All those data sets that might have given us a clue about the epidemic were too delayed. And this was the first insight showing that the epidemic was under control because it measured social contacts as they were happening. And if we look over time, this study is run, these red dots, every week. And if you look at the REACT community study, which is this regular study of infection in the community, the social mixing correlates very nicely with what's going on with community infections. So it suggests that it's not some huge accumulation of immunity that we don't know about, but actually, as people change their social contacts in summer 2020, starting to increase contacts, we start seeing an increase in transmission as a result. And we see something very similar in Wuhan social contact studies. They actually had quite a dramatic reduction. Again, these age patterns changed, but about a 90% drop. And we see something similar, actually, if you look at that whole Wuhan curve, it really did come down dramatically during their lockdown period. But overall, it shows the value of combining all of these different data sets, particularly when you're doing these models. So earlier, I showed you that model in the autumn in the UK about control measures and a potential lockdown. And in that analysis, my colleagues validated against a whole range of data sets. So everything from hospital admissions to community testing to antibody levels. And the region before the line here is them fitting the model to data. And then afterwards is a prediction of what happened next. And you can see that some of these predictions matched quite nicely with what happened next. Some of them didn't quite match what happened in reality. But they also predicted what would happen to behavior, which is a very difficult thing to predict. And if you compare with Google Mobility, the dashed lines here are what they predicted would happen. And then the other lines are what actually happened in that data set. So you can see that some of it, behavior didn't quite change as was predicted. And that probably explains some of the differences we see in the data. And of course, another thing that changed during that period is variance emerging. But without combining all these data sets, that model wouldn't have been able to distinguish as effectively between these different scenarios. So I think there's lots more to be done in this area, but really from the early stages, even to the work being done now, it shows the value of having these orthogonal data sets that can give you insights into different bits of that transmission process and different bits of the dots if you're trying to understand what's going on. So what I'd like to finally do is talk a bit about just the process of how this science is done. So I've talked about 3 different areas where modeling can provide some value. There's obviously enormous challenges in doing that modeling well, but I think there's just also logistics of how you put this modeling into practice. And I think this is a useful quote. This is from Chris Whitty, who before he was Chief Medical Officer, but he's now CMO for England. And he was talking about the use of academic papers for policy, somewhat in the context of epidemics. And that often academics, we take a long time to write papers and do studies. And in a real-time epidemic, you need those insights much, much faster. And that can cause some problems. I think this is a useful figure from a few years ago. This is from the Ebola outbreak in 2014. And the top figure is the number of sequences that were made publicly available. And the bottom figure is the cases. And you can see there was this initial release of some sequences and then this gap. So despite there being cases, despite sequences being collected, there wasn't this information being released. And actually the epidemic was over. And then you had these papers appear far, far later, which, the epidemic was done by that point. And so really, I think outbreak science, it needs to be fast, it needs to be open, it needs to be reviewed, and it needs to be collaborative. And I'd like to talk briefly about what those different things can look like. So first of all, fast. Journals can provide a number of roles in terms of peer review, in terms of oversight, but they're just simply too slow in an epidemic. A lot of the requests that we've had for COVID have had deadlines within a couple of days, over a weekend. And if you're producing that kind of work, you also want to be making it publicly available so others can use it. But even preprint servers we found were taking 5 days or more to process papers. And so we set up an online repository where we could actually get reports up quickly, we could get code out, and it just gave us more control over that research process. I think particularly getting the code available was something that was important, getting the data out there, which again creates its own challenge, because if you're trying to respond to policy questions, if you're trying to build the models, getting all the code written up and tidied when a lot of people are doing this in their spare time is enormously difficult. But when it can be done, it's useful to a lot of other people. I mean, this was some early work we did on the amount of underreporting in different countries. And a lot of journalists, other government advisors picked it up and reused it for their own data sets in their own context. So I think it's really important to get this stuff working, but of course, it's very challenging, particularly for smaller research groups to have the resources to do that. But we don't just want something to be fast and open, we also want some scrutiny of that work. So what we implemented was this internal peer review system that people who weren't directly involved in the work, but in the wider group, would review the work before it went online. And then, of course, many of us sit on advisory groups, and we would also submit to journals, but this would take a bit longer. But we had this process where, at least if we were putting something online, it had gone through some initial scrutiny and some initial feedback before that happened. And there's been other schemes in the UK, for example, the Royal Society ran a scheme providing this very rapid feedback on research. So at least there was some peer review, even if it wasn't in that formal journal system. I think the final point, which is obviously a key one, is research needs to be collaborative in an epidemic. And especially a lot of the really important things that happen aren't visible and aren't publishable. I mean, things like data extraction and cleaning that sound quite boring are fundamental to a lot of the things that I've showed you. You know, that relies on having those data tasks functioning, having code working, doing literature reviews. So we created this working group to at least make sure there's a formal structure that people could be involved in. I think there's many different versions of how we could have done it, and other groups have done similar things. But I think having that kind of way of acknowledging that work is important. And we wrote this perspective last year, reflecting that a lot of the work that's been really, really important for COVID doesn't fit into this neat journal paper model. And I think we need to consider what that means for the future. If this really important epidemic work is happening, but it isn't being acknowledged in traditional ways, where does that leave us? And just to highlight a few of the kind of work that's happened during the pandemic, there's a huge amount of data work that's been going on, but these are a few examples of people who've done a lot curating data. And in the UK, for example, there's a lot of work that goes through Public Health England in terms of the case data. The Office for National Statistics also runs these community surveys. And then Imperial have also been running a community survey of infection levels. And these are really fundamental, insights into what the epidemic is doing. But of course, these are things that had to get off the ground quite quickly in real time. They weren't there ready to go from the start. And I think we need to look ahead to the next epidemic, the next pandemic. How do we make sure these things are in place from the very early stages and not much, much later where they're useful, but we had to rely on that very patchy data in the meantime. So that brings me to my end. Hopefully I've given you at least a brief overview of those different uses of mathematical modeling, that it's not just about those big scenarios and what's going to happen next, but it's about understanding quite basic aspects of the biology, where we are currently, but also just some of the challenges of how we do that work as academics. We want this to be fast, we want it to be open and collaborative, but we also need to think about how to make it sustainable. There's a lot of people who've been doing these things in their spare time. They've been trying to find ways of ensuring it's sustainable, but we're 18 months in, some of these projects are no longer happening. When we come to the next pandemic, who's going to be responsible for it? Are we just going to rely on this sort of unfunded rapid research, or can we get things in place so we learn these lessons now? So thank you for listening, and thank you again for the invitation to speak.
Thank you, Adam, for this excellent broad overview of the modeling issues in COVID. So we are now open for questions while we. So there is, I can see one hand. So let's chat a little bit about your talk. So there is a lot of uncertainty about the future scenarios, and this is very clear to all of us. But there is one thing that we are very sure, very certain about, is that there will be a next pandemic. So given this experience, how would you structure a surveillance system? What are the key data and the key components that would help us in get prepared for a new experience like this one?
I think for me, the crucial thing is having data that is as early and as unbiased to the infection events as possible. I mean, even to give you context for the UK, a lot of the early signals were around your hospitalizations or people showing up critically ill. And that's 3 weeks too late, really, to be responding to an epidemic. So I think having those community surveillance data sets in place that you can catch things early. We're seeing now, for example, wastewater surveillance. Australia are using that as kind of early indicators that they might have a problem. So I think the more we can roll out those kinds of data sets that give you very rapid awareness. And then I think also just looking at countries, for example, in Asia that have made much more use of traveler testing. If we're in this situation, I think we want to avoid getting somewhere where countries are going into lockdowns again. I think that's a sort of response from 100 years ago. And I think the only way to avoid doing that is you need very good awareness of what your epidemic's doing, so you can focus in on where the transmission is actually happening. I think the big limitation for me last year is we actually had no idea where transmission was in certainly in most European countries. And if you get to that situation, the only thing you can do is quarantine everybody. And then that's obviously a very bad outcome for everybody.
Okay. So I have here one question from the audience is, how do we factor in fake news? How do we factor in fake news? How do we as scientists deal with misinformation in this context?
Yeah, I think that's a really good question. I think it's one that's going to shape a lot of where the pandemic goes now. I found it helpful to think of fake news and think of misinformation something like a contagion process, and in particular, a lot of people who are kind of involved in it from a sort of particularly manipulative way online treat it as that contagion process and get people to interact with things. So, for example, if people are posting things that seem a bit shocking or annoying, they know people will pile in and interact and amplify it, and then the algorithms will amplify it and so on. So I think on one level, just thinking about how we interact with those, and there's a lot of good guidance out there about actually, if that information is there, how do you engage with it in a way that's actually healthy and not just doing more damage. I think also organizations and platforms have a role to play. I mean, we saw a lot of social media platforms in this pandemic would actually put badges on misinformation, which is something they've never done before. And so I think to some extent, we also need to think about the network through which contagion is spreading. And in some cases, do we actually just need to change the structure of that kind of network? But I think alongside that, though, I would say that we need to distinguish between what's kind of deliberately harmful information and what's people just trying to understand uncertainty. I think a lot of people do have questions about the disease, about its severity, about the vaccines. And a lot of those questions, are just people wanting information. And so I think we have to be there to provide that information in quite a good, non-judgmental way, while also tackling these kind of more manipulative elements online.
Okay, so another one. Do you have suggestions or insight on what would be interesting data sets in countries where case testing and screening are very poor, such as Brazil?
Yeah, I think that's one of the big challenges, that a lot of the data streams essentially rely on testing in some form. So if you look at cases, if you look at deaths that are confirmed, a lot of those essentially come through that same pipeline. So if you don't have the testing coverage, all of those data sets will have the same problems. I think the more potential there is for that kind of community survey, so whether it's looking at antibody levels, whether it's routine screening. So some countries, data sets we've interacted with, people coming into hospitals for non-COVID reasons, just testing randomly, that gives you a slice of what might be going on in the community. And then I think in the longer term as well, work that kind of looks at wider excess mortality, for example, and correlating that can give a sense of how much underreporting there might be. So recently, after the epidemic in India, there was a lot of work comparing actually what were the patterns in mortality versus what had been reported. But I think for me, again, it comes back to that kind of that question of orthogonality, that a lot of the routine data are all going to suffer from the same problems if you've got limited testing. So if you can find ways of getting information on aspects of the epidemic that don't rely on those kind of data sources. But of course, it's challenging, because if you want to set up a a testing program that needs tests to work. But there are, as we see in the UK, with React and things, you don't necessarily need enormous numbers. You don't need to be testing millions of people. You could do a much smaller subset of your population and get some useful information.
Okay. So we had yesterday a very vivid discussion about on how to report uncertainty in our statements, predictions, and you touched on that in your talk. And we also compare the way we do it, I mean epidemiologists do it, and the way that people, researchers on climate change do. So they have a much more elaborate way to incorporate, to report uncertainty. Why is it so? Why, for example, you touched on issues like identifiability, you touched on issues like robustness, on how to achieve robust statements by having orthogonal data sets. But we don't deal very much on the uncertainty brought by model structure and the ideas of ensemble modeling and things like that. So why is it so, and what can we do in order to be more, let's say, honest, fair about the uncertainty associated to our predictions?
Yeah, I think that's a really good point, and it's something that we've probably got a lot to learn from organizations like weather forecasting. I think epidemiology is probably a younger field in the area of forecasting than weather, and I think in part that's just how it's evolved. That historically a lot of the work's been quite theoretical. In the last 20, 30 years, a lot more data has come in. But I suppose if you're talking about climate and weather, the underlying system is much better understood. So you're predicting a kind of physical weather or physical climate system rather than human behavior in the middle of a pandemic. And historically, the data sources have been much better. I think COVID is the first time we've actually had enough data on all of these different aspects of transmission to fit these things more rigorously. But I think for me, having those metrics for evaluating forecasts, I think is a really important one. I think it links back as well to those academic incentives that I think historically people have done some work, published it, and there's no incentive to go back and actually evaluate whether that forecast or that scenario is any good. So I think having more kind of routine ways of doing that. And we see it a little bit with the consensus estimates that happen. And there's some work by CDC in the US and ECDC in Europe about ensemble forecasting and trying to get groups to do that routinely so you can evaluate them every week. And I think we just need more of those kinds of structures for people to contribute to, because there's been many years of like flu forecasting, for example, and there's quite a limit to the performance just in terms of how well we understand the biology. And I think for me, getting better models of the underlying system is one thing, but then also getting a much better collaborative approach so we can evaluate what we're actually predicting and what it looked like after the event.
Okay. So no more questions. Adam, a very, very, very big thank you for accepting our invitation. We had an excellent time. The talk was really very insightful, and thank you very much.
Thank you again.
Bye.